Good afternoon, everyone. It's Catherine here from Miovision. Thanks so much for joining us for our Clear Signals 101 certification today. We're just going to give a couple more minutes for a few more people to jump online, and then we will get started in just a couple minutes. All right, I think we're about ready to get started here. So again, it's Catherine from Miovision. Thank you again for joining us for Clear Signals 101. So this is the first of our automated the traffic signal performance measures training program. So a little bit of housekeeping to start with. There is a quiz that will be sent out near the end of this session. To receive the emailed copy of the certificate, you just need to complete the quiz and send that over to us. If you have any questions as you're going through the session, you should see a question section where you can type in, and we'll read through those and answer any questions you may have as we go along. But now that's all underway, I'm going to introduce Sajad, who's going to be running our session today.
Okay, thank you, Catherine. Hello, everyone. This is Sajad from Miovision. Hope everyone's doing well and staying safe these days. Today is the first session of a multi-series webinar on ATSPMs called Clear Signals. So today is Clear Signals 101. We're going to go through sort of the fundamentals, the basics, and then go through some examples. And then hopefully in the next series of webinars, we can go through sort of more advanced applications of the data and the ATSPMs. So just to give you a little bit of background about myself, I have a civil engineering background, and my graduate studies have focused on traffic and transportation specifically. In the past 4 or 5 years, I've been specifically focusing on ATSPMs and how to use the data, apply the data, help agencies incorporate that data into their day-to-day workflow. So seeing a lot of examples from different locations. And my aim in these series is to sort of squeeze what I've learned in these 5 years from ATSPMs and present that to you, and hopefully you can take away from that. So let's get this started. So the course breakdown, what I want to do is that there's in the entire course, so the entire series, we're able to cover all of this, but today we're going to specifically focus on a number of these items, mainly starting off with the basics, what is the data, where it's coming from, what are the performance measures, and go through the explanation of the performance measures itself, because it's super important to understand what the performance measures are before ones, and where they're coming from, how it's calculated and presented before we actually go into applying it. But today, hopefully we can get into some intersection performance assessment, and we can go through some examples regarding that. So by the end of this course, so hopefully you would be able to explain what the ATSPMs are, understand what each chart shows and what it represents, being able to assess the performance of a corridor against objectives, assess the performance of individual intersections against objectives, and then hopefully be able to provide recommendations in addressing the inefficiencies themselves against those objectives. Okay, so let's start off with the basics of what is automated traffic signal performance data. I guess a lot of people already know this, but just for the sake of this presentation, so ATSPM stands for Automated Traffic Signal Performance Data. The idea is that there's a number of, so this work came out of Purdue University a few years ago, and in collaboration with a number of public agencies in the US. And the whole idea was that, okay, how can we leverage infrastructure that's already available in the traffic network to be able to generate a number of performance measures that helps understand the performance of the road network in a very high resolution format. So not to just get an idea of, okay, like travel times here are high or not, it's more about being able to identify the where, the what, and the how. So be able to identify where the inefficiencies are happening, why it's happening, and what can we do to be able to address them. So the whole idea is to be able to do continuous measurement of performance from the perspective of the road users. So conventionally, traffic engineering, we do a lot of demand measurement. So we do turning movement counts, and then we model, and then we try to model what the performance would look like. But with all this technology that's available and this connectivity, like this really creates the opportunity to be able to do less measuring demand and more measuring performance directly, and being able to use performance directly in order to achieve the objectives. And even if modeling is happening, so definitely the modeling for what if situations is definitely a need, but this data can help calibrate those models to have better representation of the true traffic conditions. So just to give you a little bit of sort of comparison between the two approaches. So in the conventional approach, very, very simplified, we measure demand, we model traffic, we sort of evaluate, and we improve and optimize. But with the new approach, or if you want to call it the ATSPM approach, the idea is that we measure performance directly, we evaluate it against the objectives, and then we make changes, improve, optimize. And really the big difference here is that there's a feedback loop. Because the data is continuous, it allows the users to sort of keep that loop going, and being able to continuously monitor, continuously improve, and keep ahead of the changes in traffic conditions, and being able to actually directly measure the changes that have happened. So let's say there's a change made, or even before a change is made. So does this corridor even need a completely new retiming or not? How have things changed in the past month or past year? And being able to understand, are there opportunities for to be able to increase capacity in this roadway or not? We're already seeing a number of public agencies move towards this approach. So even having contracts for traffic engineering firms to be able to leverage this data and provide value to the cities, not using sort of the traditional approach, but using the ATSPM approach. So what we advocate for is what we call healthy signalized intersections and corridors. And the main aim of this is to be able to help agencies achieve their objective. So a healthy signalized intersection in corridor is one that's helping the agency achieve their objectives. Could be a single objective, could be multi-objective. So let's say an agency wants to minimize delay along the main corridor, so they want to keep the main corridor flowing smoothly. That's an objective. They can use the data to be able to assess how they're doing against that objective. What are they sacrificing in order to get to that? And ultimately up to the agency to decide to give it a thumbs up or a thumbs down in terms of, okay, this is what I want to happen in this corridor. It can also help with determining the objectives as well too. So let's say there's a midday operations and the intersection is operating on a high cycle length or it's coordinated, but the data shows that there's not a lot of saturation going on the major movement. There's a lot of delay on the minors. Maybe here we can think about maybe providing more equality between the movements. So the data not only helps to assess against objectives, but it also helps determine those objectives as well too. And as cities receive complaints, this is a really great opportunity to be able to do data-driven measurement against those complaints. So someone says that if a city receives a complaint that someone is stuck behind the left turn signal and they're waiting for a long time, sometimes the user itself, the road user itself, might not have the complete context around what's happening. So this is a really great opportunity for agencies to be able to look into those complaints not from a subjective perspective of the road user, but from an objective perspective, and understand what was the context behind it, and then be able to understand whether there's an opportunity to actually address the situation. So in terms of achieving those objectives, we, based on what I have seen, technically we need to assess the performance of the traffic signals from 4 perspectives, and then these sort of work hand in hand. Starting from maintenance, so a simple example of that would be detection. So if detection is working properly, we can sort of think about the next level. But if, for example, there's a stuck detector, and then it's just there's not a lot of demand, but the detector is either broken or stuck, and it's just maxing every cycle, regardless of how good your timing plan is, that problem is going to create a lot of issues performance-wise. So super important to be able to address those maintenance issues before we even think about sort of the next level. The next level that I've seen are operational type of problems. So operational type of problem are the bucket that the types of problems that are prerequisites, in my opinion, to an optimized plan to work properly. So some of the, so for example, phase termination issue. So either passage times being too low or too high, minimum greens being too low or too high, or some kind of other issue, or in coordination. If you have in a corridor that's supposed to be coordinated in both directions on the major, if you have 2 intersections that are operating on a completely different cycle length, although they're constant cycle lengths, that's going to create issues for coordination. So regardless of how good your offsets are, if you don't have those cycles lined up properly, and this is a common issue that I've seen in a lot of corridors, if those cycle lengths aren't constant along the corridor and the same value in that time of day plan, we need to fix that before we even think about optimizing offsets. And then the next level is sort of optimization, where everyone talks about, like split cycles, offsets, time of day plans, where the duration, and then ultimately safety. And I think this is a very important one, and the previous ones really help with this one as well too. So it has been proven that optimized traffic signals that are well timed and according to demand are actually safer as well. And then being able to generate, and I'll go through this in a little bit, where ATSPMs aren't just what's now, there's a lot of opportunity for it, and then safety is a really big opportunity to be able to follow through and being able to add performance measures that not only look into the performance of drivers, but vehicles, but also other road users. And then that sort of these items go pertain to the data and the type of data that's being collected. There's also another element to this data, which is the continuous nature of it. So why does this data need to be continuous? Why can't we just get a snapshot of it? So the reason that in my opinion, the continuous value really comes from, I've tried to show that in the bottom right corner here. So the true value of the continuous nature of the data comes from the fact that you can monitor all these different types of problems that can happen and being able to address them sort of bit by bit and eliminating the need even for a major signal retiming in a long while. So let's say if there is even a major signal retiming that happens, and if let's say we have a performance health rating or score, it's really good now, it's in the green area, and as time passes by, things happen. Detectors fail, maybe one intersection starts to have some clock drift issues and creates coordination problems. Traffic patterns start to change and there's split allocation problems. So as time passes by, that health rating will start to go down. And if those issues are addressed bit by bit, you're not only able to, with the small amount of effort, being able to keep that intersection and corridor nice and healthy, but also being able to reduce the need for a major signal retiming in a long while. So let's get into the ATSPM data. So where does the data come from? I think it's important to understand where the data comes from and what is combined with what data to be able to generate the performance measures. And that way, I think I found this to be really useful to understand where the data is coming from to be able to interpret the graphs properly. So one of the main sources of the data is coming from, of course, the traffic controller. I'm simplifying this as much as possible. There's definitely a lot of details in there, but you could imagine that from the traffic controller, the most simple information data that's coming is the amount of red, green, and amber that's being allocated to different phases. So that would be phase interval graph, being able to see how much that is, being able to extract timing plans, phase termination. So did this phase max out? Did it force off? Or did it gap out? So what was the termination reason? And then some interesting ideas around being able to, which I'll show you in a bit, is okay, we have the phases, why don't we just line them up in a time-space diagram, and you can actually see an actual time-space diagram that's happening in the field. So not a theoretical one that's in a simulation software, but an actual one of what is going on out there, not just what's theory on paper. The next data is coming from detectors. So detector activations, this doesn't need to be, could be technically any technology that's providing actuation at the intersection, or any kind of detector that's available at the intersection, even if it's for data purposes. So you can imagine one of the basic ones would be stop bar detectors. And then some of them could be advanced detectors, which are further back from the intersection. So although their main purpose might not be data, but they came up with some very interesting ways to be able to understand the performance of the intersections and corridors by either using this data on its own or combining it with the signal status data. So you could imagine a vehicle that's arriving on an advanced detector. If you combine that with the signal status, you can get a sense of arrivals on red or arrivals on green. Or if we get a sense of the occupancy ratio of this stop bar detectors on each individual movement, we can get a sense of the level of saturation that a movement has. And I'll get into the details a little bit more. So there's a number of performance measures that comes from combining these two pieces of information together. There's also some data that could come from the detectors just themselves. That could be, for example, volume. So there's an advanced detector. As vehicles are passing on it, there's the detector goes on and off, and then that could be counted as one vehicle. So sort of the arrivals or the approach volume or demand can be measured this way. Or another piece of data that could come from detector activations or pedestrian button usage. So that's an interesting one as well too. So how often is the button being used? Sometimes it helps understand like when the button is stuck and it's constantly giving pedestrian walk signals, and also being able to get an understanding of the pedestrian delay. So from the time that the pedestrian pushes the button to the time that the movement, that crosswalk gets a walk signal, we can sort of measure that as the pedestrian delay or simple delay, if we want to put it that way. The third piece of data that's available is travel time. So through Wi-Fi MAC address data, through Wi-Fi MAC address sniffing, the MAC addresses are anonymized, and then they are matched from one location to another. And then that way, it's possible that we run that data through a filtering algorithm, and then that way we can get travel time information for a number of vehicles. What we found out is that it's around a 16% sample size, which provides statistically valid average travel time readings in 15-minute intervals. So from that, we can get travel time, we can get speed. There's another metric that we can generate. It's called congestion scan that I'll go into a little bit, which provides the travel time, visualizes the travel time information on a corridor level. And then we can get the different indexes like the travel time index or the reliability index. Apart from that, and I think this is what really opens the door to a number of other ATSPMs, and really there's no limit to it, is computer vision and what that enables. So performance measure or ATSPMs are mainly focused on vehicular performance, and the reason is that the detection that's out there is mainly focused on vehicles. And totally understandable that some locations, the objective is that, and that's totally understandable. But if the agencies have other objectives, computer vision really opens the door to be able to do a multimodal performance measurement, and to be able to assess all sorts of different types of objectives in the road network. So I'll go through a couple of performance measures that we've generated using computer vision and how sort of that fits within the narrative. So you can imagine here, just a visual here. This is the signal phasing and timing that's happening. On the left, you can see the detector. So this is the basic piece of information that's coming in, and you could imagine how combining these pieces of information together, we're able to generate those performance measures that we're talking about, that I'll get into a little bit. So in terms of intersection assessment, so before I get into the performance measures itself, I think it's good to sort of understand what are we trying to achieve here and what are we trying to assess. So the intersection, in terms of intersection assessment, there's really three, again, like those three main areas that we talked about: maintenance, operations, and optimization. We're talking about the signal working itself, obviously, detection and communications. That's important on the maintenance side to be able to assess. On the operations front, for intersection level assessment, we're talking about phase termination. So making sure or assessing that different movements at the intersection are terminating properly. That's super important. So we don't have left turns, for example, that are actuated and are wasting green time. That's not a good effective usage of time and space at the intersection. From an optimization perspective, being able to assess the performance at an intersection in terms of the green split, in terms of the mode of operation. So does it need to be coordinated here, or is it possible to do like free mode here, like that sort of thing? And I think that needs to be looked at individual intersections, but we can call that an intersection assessment. And then force off modes as well. Floating or fixed force off can be determined using the data. The approach that I found to be useful is using a checklist approach. Again, it depends on what the method that you like, but I found it to be pretty effective when you set a number of criteria, and then you sort of assess against those criteria. And if there are cases where it sort of needs to be flagged or further looked into, you can flag them. So this is sort of a triage, if you want to call that, and then sort of starting to dig into some of these items and figuring out, okay, what's going on? Is there something that can be done about it? And that sort of thing. Okay, so let's get into the traffic insights. So there are a number of traffic insights again that we talked about, and it's all coming from those data sources that we discussed. And let's get into the performance measures themselves. So I'll try to go through this as fast as possible, just so we can go through a number of examples. So let's start off with the corridor congestion scan. So the corridor congestion scan, this is a graph that is coming from, the data from this graph is coming from travel time data. So the Wi-Fi data that we talked about from intersection to intersection. One of the ways that the data can be visualized, the travel time data can be visualized between different intersections in a corridor is the congestion scan. So basically what you're seeing on the screen here, there's two sides to this graph. One is showing one direction, so it's showing, let's say, westbound, and the other one is showing the eastbound or northbound or southbound. And then there are different sections within this corridor. And then basically what it's doing is that each of these slivers of time is a representative of 15-minute duration, and it's showing the median travel time between these two sections of the corridor in this direction in this time of the day. So this is around 8 a.m. and it's showing us the travel time index. So what is the travel time index? The travel time index is the average travel time over free flow travel time. So it's telling us, and in our system, we have a lot of configuration capabilities. So you can run a day, you can run weeks, you can run months, and aggregate all of that information. So basically what it's saying is that, for example, midday, just by a quick view at this corridor, you can quickly identify where is the bottleneck, how bad the situation is, and where and when it's happening. So for example, this area where it's yellow, it means that the travel times in this time of the day, in this section of the corridor, in this direction, are almost 3 times free flow travel time. And then the rest of the day, the rest of the sections almost look actually pretty good. So the travel time index allows us to compare sections of different sections of a corridor with each other, even if they have different lengths, even if they have different travel times, because it's being divided by the free flow travel time. And then this is travel time index, and then we have the travel time exception index as well too, that can be switched to. The travel time exception index compares it to the past 4 weeks. Planning index is the 95th percentile over the free flow. So it's more of an indication of it's more of an indication of the reliability in travel time. So how are we doing in terms of the variation in travel time? Another performance measure is point-to-point travel time. I'll try to go through this as fast as possible so we have time for examples. So point-to-point travel time, pretty much the data that we talked about in the congestion scan. The data can be looked at from an intersection to intersection perspective. So for example, let's say it was the last time that was detected at intersection number 1 and the last time that it was detected at intersection number 2. We get those data points, we run those orange lines through it, that's showing the median, and then be able to do aggregate statistics on it as well to not only look at one day, but be able to look at multiple days. So my favorite graph, the split trend graph, this one needs a little bit of explanation. So basically, this graph shows the performance of each individual movement at the intersection that have stop bar detection. So basically, I think on the left we have a simple explanation of that. So let's say there's a stop bar and there's a queue of vehicles waiting to pass through. They get the green light, they pass through, and then just at the start of the red, there are still like 3 vehicles remaining, and they weren't able to clear the queue, or what's called a split or cycle failure happening. So using that occupancy ratio during the green time and during the first 5 seconds of the red, so on the bottom right corner here, so we have a green occupancy ratio that's happening during the green time, and then we have a red occupancy ratio, or what's called an ROR 5, during the first 5 seconds of the red. And each cycle, basically these circles, will fall somewhere within this graph. So it can't be outside of this, it will be somewhere within this graph. And then what Purdue University did was they start to divide this graph into different sections based on sort of looking at all sorts of different scenarios, and I think it's a good it's a good way to divide this, and it's usually shown the true performance, is that, for example, if the stop bar detector is occupied more than 80% of that green time, and just at the start of the red, it's still being occupied, you're going to have a cycle that falls in the top right corner. And that would be sort of the red zone, or what we call a split failure. And then every other sort of area within this graph is a representative of other categories here. So let's say if there's a queue, they were serviced properly and then terminated, no one remaining, we're going to be sort of in the OK zone here. So they were the movement was serviced, extended, and terminated properly. We're going to be in this green area. So we're in this yellow area, for example. So low green occupancy ratio, not a lot of arrivals during the green time, and then just at the start of the red, there's a vehicle arriving. Sometimes this could be an indication of coordination problems. So you could imagine this could be like a green starvation that's happening in this case. And what we do is that we take this bottom right graph and then we visualize it using a stacked bar chart format that you can see on the top there. So each of these bars represents a 15-minute duration, and each of those height of the bars in each category represents the number of events or cycles that are within that category. So you could imagine, just by looking at this, let's say this was the westbound through movement, you can easily tell that this movement starting from around 4 p.m. to 6 p.m. is experiencing a significant number of split failures. Now in this graph, we might be just looking at the split failures, but we might be also the blue area might be also important as well too. So we don't want movements that need to be serviced, extended, and terminating properly are not doing that. So you can imagine that if a left turn movement, so you could imagine if there is a left turn movement that that needs to terminate properly and is actuated, is showing a lot of blue or spare capacity, that's a bad sign, because it's showing that that movement is wasting green time. So this is sort of the graph. I just wanted to explain that in that context. There are other graphs here as well too that I'll quickly try to go through. So approach volumes, we talked about sort of the advanced detector. So if an advanced detector is available at an intersection, we can read the number of on and offs on the detector and being able to aggregate that and visualize the approach volume. So this is not the turning movement count, it's more of a sort of an arrival as opposed to a turning movement count. We have arrivals on red and green, so you could imagine that volume data that we talked about. If we take that volume data and if we take that volume data and we correlate it with the signal status, we can get an understanding of the number of vehicles that are arriving during green, the number of vehicles that are arriving during red, and this is one of the ways that we can visualize that. So a really good way, especially if you also have a model, to be able to compare and see is really what you have on paper really happening in the field or not. Phase interval, another important one, which is basically just showing us the amount of red, green, and amber that's being allocated to different movements at the intersection. The good thing about this is that by turning off and on sort of the red part, you can actually see which movements are maxing out, which movements are how often the movement is gapping out. It's also possible to see the cycle length. So if an intersection is coordinated, the phase interval graph on the coordinated movement would actually show the cycle length that's happening throughout the day, and be able to assess that, whether the controller is able to keep that cycle length nice and constant. Are the different cycle lengths constant throughout the corridor for that time of day plan or not? We'll get into examples in a little bit, and then I think you'll get a better understanding. Product coordination diagram, this is another one. Again, the vehicles that are arriving on the advanced detector, if we correlate that and overlay that with the signal status, we get a product coordination diagram. So you could imagine that each of these black dots that you can see on the screen are representative of one arrival of a vehicle on an advanced detector overlaid on the signal status. So every dot that's showing up on the green area is an arrival on green, and every dot that's on the red area would be an arrival on red. The advanced detector needs to be further back from the queue. Sometimes it might show that you're seeing a lot of arrivals on green, but not a lot of arrivals on red, whereas the queue has actually passed over the advanced detector. So recommend for the advanced detector to be further back. Occupancy ratio. So we talked about those occupancy ratios on the stop bar detector. One way that we visualized that was using the split trend or the split failure graphs. Another way to be able to do that, to see that, would be the cycle by cycle occupancy. So it's spare capacity or OK zone or I don't know, split failure, but how much is it? Like I want to actually see how much occupancy, and this could help inform some of the opportunities for reallocation of green time to be able to really understand, okay, yeah, it's sort of spare that the other movement has spare capacity, but how much? So this would help assess that. The split analysis, like the split failure that we talked about, again, one of the ways that we visualize using that stacked bar chart format. You can also choose to see the data in this format, so actually see where each cycle sort of falls into. Simple approach delay. So simple approach delay is not the actual average delay of a movement, but it is the amount of time from the arrival on a vehicle on the stop bar to the time that they get a green light. So you could imagine the maximum amount of simple delay could be the amount of red that a movement is experiencing. Green allocation. Green allocation shows the percentage of green time that's being allocated to different movements. So sort of different southbound, westbound, northbound, eastbound. What is the percentage of green time that each of these movements are receiving compared to each other? So it's a good opportunity to be able to assess the movements against each other. Pedestrian delay or pedestrian simple delay. This is, again, one of those graphs where each bar represents the time from when a pedestrian pushes the button to the time that the pedestrian actually gets a walk signal. And this also sort of implicitly also shows the number of times that the pedestrian phase is being called. Another sort of functionality that we have in the system is a corridor report card. So again, being able to assess all of these on an individual sort of metric by metric or intersection by intersection is difficult, but how can we sort of look at more, how can we have a more holistic view towards that? So as the report cards can help with that. So being able to compare, let's say, the last month to the month before that, or the last month to the same month last year, for example, and being able to understand, okay, sort of get more of a dashboard view of how have travel times changed, how have this number of split failures changed, or delay, or be able to, so all of those different metrics that we're talking about, and be able to get an understanding of sort of where would be some of the pain points that we should now start to sort of dig into and figure out what we can do about them. And then these report cards are available sort of on an intersection basis, and they can be available on a corridor basis. So intersection level, we're more talking about like the simple delay, we're talking about the split failures, and at the corridor level, we're more talking about travel time and arrivals on green and red, and that sort of metric. Another metric that I talked about with the time space diagram. So you can imagine this is a time space diagram that's actually happening in the field. It's not grabbing the timing plan, or it's actually this is what's happening in real time with the time lined up together. Being able to understand what the green bands look like. This is a really good opportunity to again assess these against what you have in your model, or if you don't even have a model, it's really good to be able to assess the consistency in coordination. So a lot of cases I've seen, oh, coordination sort of looks good in the first 15 minutes, but as time passes by, it seems like something's drifting, and then it's really impacting the green bands. And so really good check with that. And then this could work hand in hand with the arrivals on red and green or the coordination diagram. So being able to see, okay, based on my time space diagram, it seems like we should have a significant number of arrivals on green here, but we actually have a lot of arrivals on red. What's going on here? And being able to sort of assess coordination. This is where we get into more of the computer vision side, where not only sort of seeing those volumes, but being able to see the volumes of bicycles, trucks, pedestrians, vehicles, and being able to assess that. So this is where sort of the multimodal aspect that computer vision brings. This is just a comparison of a traffic during a weekday in downtown Toronto compared to a Raptors parade last year. Another metric that sort of, again, computer vision really brings in the capability to do this is the red light running graph. So red light running, it's basically the amber behavior and red light behavior. So each of these dots represents one vehicle being in the middle of the intersection. So we classify, track the vehicle, we classify the vehicle, track it, and somewhere in the middle of the intersection, we take a snapshot and correlate that with the signal timing. So each of these dots represents those arrivals of vehicles in the middle of the intersection correlated with signal timing. So you could imagine all these dots that are further high. These would be cases where a vehicle or a cyclist is running a red light. And then we have sort of the aggregates of these as well. Another metric that, again, computer vision really brings in to the table is pedestrian compliance. So pedestrian signal compliance. So again, imagine each of these dots represents one pedestrian that is in the middle of the crosswalk in different times throughout the day, correlated with this pedestrian signal status. So the yellow area is actually the flashing don't walk area, and the red area is the static don't walk. So all of these dots that are within the red area are representative of a non-compliant pedestrian. So it's interesting to be able to assess the performance of intersections. So when a retiming happens, when there's an increase in cycle lengths, when there's preempts, how can we assess like how these are starting to impact pedestrians, and these directly correlate to the safety of the vulnerable road users. Okay, so let's get into examples. So let's get into an interesting example here. This is an intersection that had two LRT trains running through it, two lines of LRT, and this was an interesting one where we sort of have it before and after. So we have a time where the trains weren't running, and then we have a time where the train started to run, and really helped to do sort of a before and after analysis of how the train preempts are impacting traffic, and whether there could be something done about it. So one of the graphs there is actually the preemption graph. So being able to see on which movement, what are the duration of how frequent the preempts are happening firstly, and then where are they coming from? Is it like emergency vehicle? Is it an LRT? Is it a train? And then being able to understand the duration of them. So you could imagine in this case, the trains are pretty frequent. And then there was, and the city staff already knew that, yeah, this is going to have an impact on traffic here. But the data really helped to be able to get a bit deeper understanding of how much of an effect are we looking at. So the good thing here was that we actually had the before after data. So you could imagine in the before condition, the northbound through movement, nice and coordinated throughout the day. Cycle lengths are nice and consistent. But as you could see in the after duration, when the train started to run, those preempts really had an impact on this intersection. So you could imagine that all of those cases, all those cycles that you're looking at, these are cases that probably the controller is trying to get back into coordination, but because of the frequency of the preempts that are happening, it seems like that's rarely happening. So basically here, again, this totally depends on the agency objectives and what they want to achieve, but one could think that, okay, in a case like this, maybe coordination doesn't make sense, right? So maybe you can allow this intersection to operate in free mode. So this data really helps the agency sort of think about their objectives. So you can see here that another issue that was happening here was the northbound left turn movement. So northbound left turn movement, we're looking at the simple delay graph here. So how much time they're actually waiting to get a green signal. The lower graph, this is an interesting one. The staff sort of suspected that this is a problem, looked into the data. Some of the delays were pretty high. So because of the way that the sequencing was put in place, they decided to sort of give some more priority and sort of reservice the northbound left turn movement in the same cycle before a preempt happens, if possible, and to be able to reduce the amount of delay that the northbound left turn is experiencing. So you can see here that when that change was put in place, we have the before condition is the top graph here, the lighter blue, and the darker blue is when that fix was put in place. So a significant reduction in the amount of delay that those northbound left turn vehicles were experiencing. And then the interesting thing is that from a signal phasing perspective, you can actually see those reservices. So all those tiny cycles that are happening, those are all the cases where that reservice is actually kicking in and coming into effect. So sometimes when I think, okay, is that really working or not? So being able to assess that, how frequently that's happening. So this really allowed to understand the frequency of that. And then from a impact perspective, in the before conditions, we were looking at the top graph, which a significant number of split failures were happening on the northbound left turn movements. Staff were sort of already aware of that, but they were able to, this is the beauty of the data, to implement something. Let's go back to the data. Let's see how much of an impact that had, whether we were able to address the problems or not. So you can see that a significant reduction in the number of split failures happened with that, with the change that was made. So this isn't easy. So sometimes this could be used to assess something, identify the symptoms, but even if a solution is put in place, immediately after that, a few days after that, you can come and assess and see how those changes impacted the performance. And then not only be able to sort of visually see that, but be able to compare that with the report cards. Okay, how much of a change are we looking at? And then the split failures on all the different movements at the intersection. So we're not just looking at one intersection here. So through the report card, we can actually see that, yeah, there was like around 26% reduction, 25% reduction in the number of split failures that was overall happening in all the movements at the intersection. So a great win here. So another issue, so again, as I said, you can sort of, when computer vision comes into play, you can start to assess the performance from other perspectives as well too. So for example, in this case, there was a movement that was experiencing a number of non-compliant pedestrians, and they were apparently happening during the preempt. And this is actually an example of that, which is quite interesting. Just showing the video here. So basically this movement that you can see on the left, they have a green light, and this movement is supposed to turn red only when there's a pedestrian call. So it's not in conflict, or if there's a train in this direction, but generally it's not in conflict with the train that would come further up. So you can see here that the data was showing actually the number of non-compliant pedestrians on this crosswalk, which was quite interesting. And then we were sort of able to use the video. Okay, yeah, it seems like this is happening. And when we started to look into the phase interval data, we were able to see a number of cycles. In a number of cycles throughout the day, there was these very, very short reds that were happening on the westbound through movement. So I don't exactly know what the problem here was, but there was some kind of issue with the preempt that was being put in place on the other movement, and it was causing these 5-second blitz of red that was causing pedestrians to think that, oh, it seems like the traffic is stopped and I can pass through, safe to pass through, but it was only 5 seconds. So staff were able to like use this data to be able to understand like, when is this happening? How frequent is it happening, and then be able to put a solution in place and address the problem. And then that problem, again, had a safety impact. Another one, another example that I want to go through, again, this is just assessing the performance of individual intersections from different perspectives. This is an intersection that was sort of on a major highway, sort of near residential areas. There was also a middle school nearby, and then the devices were installed and the data started to come in to be able to assess the performance at these intersections. So first of all, being able to sort of see from a computer vision perspective, what the volumes look like, where are the peaks happening. There seem to be 3 peaks at this intersection, considering there was a morning peak and then probably a school peak here and a PM peak, and being able to align the time of day plans with the amount of demand that's happening at the intersection. But generally, again, when I talked about earlier, we talked about sort of that health check. Let's assess sort of the intersection from different criteria. And the idea is sort of go from the left to the right, right? So from the cases where there seem to be 2 problems to no problems, and you start from the symptoms and you sort of work your way through. So just wanted to show an example of that. Again, this is at an operational level. So a movement, that left turn movement, at this intersection, the northbound left turn movement, which I've shown with the red arrow here, this is a movement that is a lagging left, so it's an all lagging protected left. And this movement, again, it's a minor movement, needs to be serviced, extend, terminate properly. What the data was showing was that immediately sort of popped out was that it seemed to be a lot of spare capacity on a minor movement. So this doesn't look good. So if this would look like 80% greener than this, would have been okay, because it shows that this movement is being serviced, terminated properly, and using its green time effectively. But when I'm looking at this as a red flag for me, what's going on here? Why is this a minor movement that needs to terminate properly not doing that? And you could imagine that when a northbound left turn movement is wasting green time, that means more delay for the southbound through. So in this case, you could see that from around 10:15, 10:36, this northbound left turn movement just remains in green, caused a lot of delay for the southbound through movement, and these vehicles need to basically wait another complete cycle in order to get a green light. So in this case, what ended up doing was that southbound through was put in reservice. So if the northbound left happens to end faster or earlier, let's enable the southbound through to be able to use that extra green time one more time within the same cycle before we sort of go to the next one. So this is an example of that. So you can see that the northbound left turn vehicle is waiting here. It's a lagging left turn. The opposing movement turns red. Northbound left turn gets its green light. It's being serviced. So previously what would happen was that this would just remain in green, right? So as the northbound through vehicles are going, northbound left would be green as well too. But in this case, southbound through actually is reserviced again. So again, these vehicles, it reduces the need for them to wait another cycle. So in terms of sort of, that's a visual way to see the impact of it, but what does that mean in terms of the impact? So you can see here, we're seeing a much more green, much more effective usage of the green time with the northbound left turn movement. And although it seems like a pretty simple solution, or it doesn't seem that much, it's about a 40-minute extra green time, unlocking 40 minutes of extra green time over 6 critical hours throughout the day. So every single day, this is unlocking 40 minutes of extra green time that wasn't previously available and now is available. So you can see that from the split trend graph, but we can also see it from a green allocation perspective. The top dotted line is showing the percentage of green time that was previously allocated to the southbound through. The bottom line is showing the green time that was previously allocated to the southbound through movement, and the top one is showing the green time that is currently being allocated to the southbound through. So almost an increase of 11% more green time allocated to the southbound through with sort of a simple fix here. Another example, so in the area of, like, let's say optimization, if we want to call it that, same intersection, westbound through, again, during that AM peak and that school peak, there were a number of split failures that were happening at the intersection, as you could see here. It's always comparative. You can't just look at one graph and say, okay, yeah, I can fix this. You always need to look at the competing movements. You always need to assess this within the context of the ring barrier diagram, the phasing sequence, to be able to understand whether there's opportunities to be able to sort of shave some time off from another movement, give it to another one, or maybe increase the maximum greens on one movement if it's operating free mode. So in this case, There were a number of split failures happening. Video is great because you can actually go back to the video and assess that during this time, this is happening, how bad is it? And then being able to run trends on the data. So what you're seeing on the screen here is actually a 2-week trend. So not just looking at one day of data, let's look at a trend and see whether this is actually something that's happening continuously. So in this case, we can see the southbound, northbound through movement, especially with the fix that was put in place with the southbound through. There's extra capacity on the northbound, southbound, and there's a possibility here to, okay, there's an imbalance in performance. Again, goes back to the objectives of the agency. One agency might be happy with this and say, you know what, I want to keep the northbound, southbound operating properly and keeping that flowing nice and smoothly. Another agency might say, no, this is something that I want to address. So this is the objectives that I think that really matter in terms of making a decision. That's why keeping the engineers in the loop is so important, and keeping the city and agency staff in the loop, because they are the ones who make these decisions. So in this case, what did we do? We look at the phase interval graph. Previously, you can see all of those green times. So this is a phase interval graph that you're seeing on the left here. All of those green times that are maxing out there, they are the ones that there are the cycles that are creating those split failure problems. It's going up to 40 seconds. The maximum time was 40. You can see the same thing happening around 3 p.m. In this case, the intersection was operating in sort of free mode. What ended up the agency doing was to add, I think it was at 5 seconds. Was either, yeah, it seems to be 10 seconds of green time for 40 to 50 seconds. And then let's see what happens. So they implemented that, and then as you could see, the same movement, we're looking at it here, the northbound left, the westbound through, or the westbound left turn movement. You can sort of visually clearly see that the number of split failures have significantly reduced and has addressed the problem. And then, yeah, again, video helps to sort of assess how that's looked like. So compared to the previous situation where we had a pretty long queue waiting again and not being able to clear, in this case, the movement is able to clear nicely. And then this happened without really impacting the northbound southbound movement. So I haven't brought the graph here for the sake of simplicity, but yeah, it didn't have a significant impact on that movement. And then if it even has a significant impact, that's fine. That's the good thing with the data, is that you can either revert back, you can change that 10 seconds to maybe 5 seconds. You can come up with different ways to be able to address that. So it's not a one-time shot. You can try different strategies and see which one really provides the best solution. So I think I'm going to stop here. So hopefully in the next session, if we have, hopefully we're having one, we can go through sort of more advanced features. We're not going to go through the basics anymore, and we can get through more examples, hands-on examples, and sort of get into more corridor level performance measures, and getting into, you can actually do, I will show you how you can do a complete signal retiming for a corridor without the need to collect turning movement counts at all the intersections. So those are some exciting things coming up. But yeah, thank you for listening. Really appreciate it. If you have any questions, we're here to answer. So if you do have questions, feel free to write it in the question box or chat box, and we'll try to address them as much as we can. How are the pedestrians being detected for the pedestrian compliance tab? So the way that the pedestrians are being detected is using computer vision. So the computer vision technology is detecting, classifying different movements. So let me just show you a quick sec here. So up over here, there we go. So you could imagine here that using computer vision, we are detecting, classifying different modes of traffic, light vehicles, pedestrian, bicycle. You can actually see a pedestrian here that's being classified as a pedestrian down over here as well. And then we're detecting it, classifying it, tracking the pedestrian, and we know where it is at different times. And then we're correlating that with the pedestrian signal status, and then that's how we get the pedestrian compliance, the signal compliance. Let's see. I'm trying to go through the questions here. Sorry, just having a hard time opening this question tab. It's very small. Let's see. Question. Oh, okay, got it. Okay. Great measurement possibilities. Sorry, just the questions are coming through. So, what is the source of the? So it says, will you be sending a file of the presentation? Sure, we can send that, no problem. What is the source of the Wi-Fi detection? Cell phones or other probes? It's mainly cell phones, I would say. So either the vehicle also has a Wi-Fi. If the vehicle is Wi-Fi enabled, we detect that as well too. So pretty much any device that's in the vehicle, it runs through a filtering algorithm. So if it's just some kind of, I don't know, a Tim Hortons or something that's pinging the Wi-Fi sniffer, then we filter that out. What are the measurement of effectiveness for the preemptive movement shown in the example here? So measurement of effectiveness for the preemptive movement. So the measurement effectiveness there would be understanding how it's impacting coordination. So for coordination, we need to have consistent cycling. So in that example that I showed, the preemption was having impact on the controller being able to keep that cycle length constant. So without a constant cycle length, basically coordination is going to be random. And another performance measure there was the split trend or the split failure. So understanding how the train operations are impacting the level of saturation and the amount of delay that the different competing movements are experiencing. This was very helpful. Can we get access to the recording? Thank you. Sure, we can do that. The slides look like a good summary of performance measures. Are these summarized as neatly as your ebook, or can we get a copy of the slides? Sure. Most newer mobile devices use randomized MAC now. So how can you track the same device? So basically what we've seen from the randomization is that the randomization isn't that frequent to not get like a travel time reading between two locations that are nearby. So what we've seen is that, yeah, for OD, for example, origin destination, that's going to have an impact because it's probably being randomized. And then based on what I've seen from travel time in general, you need a relatively small sample size in order to even in the range of maybe 10% or even less to get a statistically valid travel time reading. So even if we get rid of those, there's still sufficient amount of data to get a good reading. Is all the data available automatically to the customer from the portal? Is it a request? No, it's available. So it's available in the portal. It's called the traffic link portal. All of these graphs that I've generated, I have not generated those myself. These are all generated through the system. So great question. No, these are generated through the system. And actually the portal is much more interactive too as well. So in this case, they were all static images, but in the system, they're actually interactive. You can zoom in, you can zoom out, you can see timestamps, you can see numbers and that sort of thing. Inference from the data came through multiple sources are good, but its factual implication on mobility and safety may be discussed with a better presentation. Sure, this is just again, this was more of a 101 if we want to call it that. Please attend our next series. Hopefully we'll have more to discuss there. In COVID pandemic, how can we get TMC of an intersection where we are doing the signal study? So if you do have a smart sense at an intersection, that camera that I'm talking about, you would be able to get that turning movement count. Again, interested in the slides. I have a question on TMC, but I can't see the question. How long is the yellow time? I don't know which problem we're referring to. Sorry, hopefully I can answer that later on, and I'll send you an email. How can we get a hold of the ATSPM data collection? So please contact us. We'll be happy to help. I think it's out of the scope of the context here to be able to go through that. How accurate is PED detection? Yep, we've done quite a bit of pedestrian detection count accuracy studies, and we are very accurate. It's plus 90% at the moment. Great measurement possibilities. Great measurement possibility. What strategies are available to improve performance? Improve performance one, I don't quite understand what the question is here, sorry. Do you have a timeline for the next one? So the next one will be running in fall, so please stay tuned. Do you filter out side street left and right turns from being captured in the red light running stats? No, you can add the right turns if you'd like. In this case, I was just showing the throughs. Can computer vision place a PED call in place of traditional PED button? Can computer vision do that? Yes. Can we do it now? Not yet. There's some questions around cost that we can get back to you on those. But I want to be there's a lot of questions, but I also want to be respectful of everyone's time. So thank you so much for listening. Stay tuned for the next series. Hopefully we'll have more thorough discussions on this ATSPM data and being more interactive. So thank you for listening.